Next, let's look at example 3.14, which is on page 239. I would like you to do this as part of the homework. It's fairly long, but straightforward. No, I don't think there's much to it, and you just have to grind through it. It's quite a bit of grunt work. You have to you have to set up the the continuity and then set up the derivative in order to trap the values b and c, and that's about it. So let's move along. Next, we go to page 241. We're looking at higher order derivatives. What does that mean? The higher order derivatives are when you take the derivative of a derivative, which is not that impressive if you think about it. And when you figure out what a derivative is, right, you can always take the derivative of that, and then you can take the derivative of what you crank out and keep going. You can do this indefinitely. And the notations of the higher order derivatives are the first kind is f prime. So say you have f of x, okay, and then that's the original function. F prime of x is your derivative, and then f double prime of x, the second derivative, and this goes on to, I don't know, a million derivatives. It doesn't have to stop. There are and another way of saying it is your original function is called y of x, or just y. Let's say just y. I think most of often called y. Okay, your original function y equals to f of x. The derivative is called y prime. Okay, and then the second derivative is y double prime, and so on to a million or more, however many you need. And then the next definition is the derivative is also called dy by dx. Remember, this just means y prime. This is not a fraction at this point. So and then the second derivative is written slightly different. Notice it's called d squared y by dx squared. The second, the number 2 is in front of the d up here, but in front of the x down here. Why? Tradition. All right. And similarly, the third derivative is d3y by dx3, and so on. This goes on to a few million. So the point of telling you this is when you see this, do not be surprised. Say, wow, what is that? It just means the second derivative, and so on. So you recognize it. It's a form of notation. There are 3 or maybe even more. Actually, I think that's about it. These three standard ways of describing derivatives of each order is a tradition to have 3 different ways of saying the exact same thing. Sometimes it's convenient to pick one over the other depending on the circumstances, and we'll see more of that later. So next, example 3.15, which is, I assigned that as homework. I'm not going to cover it here because it's fairly straightforward. It wants you to take the derivative of a quadratic equation, which we have done similar things already. And after you're done with that, then take the derivative of the derivative. And you continue to crank it with the standard formula, right? Yeah. And so please do that in your homework. And then, having said that, let's move on. Example 3.16, the acceleration. This is a somewhat of a word problem, not really. But the acceleration is something that is to do with the second derivative. The first derivative is the speed, which is called velocity in physics. And then the second derivative, when you take the derivative of the speed, is called acceleration. Now, when you think about acceleration, which will come up quite a bit in our calculus derivative classes, acceleration, remind yourself of Harry Potter on that bus, that triple-decker bus, where there was so much acceleration and deceleration, where the driver is constantly stepping on the gas, so that Harry is tossed back, and then he slammed on the brakes for no reason, so Harry is tossed forward. So much fun. I mean, so that's acceleration. Acceleration isn't the velocity itself. Is how much you are changing it, stopping or starting. So you can have a lot of velocity, but very little or no acceleration. Like say a Japanese train, the bullet train in Japan goes what? I don't know, 150, 200 miles an hour or something. That thing goes, maybe more. That thing goes incredibly fast. But it goes at a steady speed. So you sit on it and you're not getting tossed around like Harry Potter on that bus, right? So that thing has very good speed, but zero acceleration most of the time. Whereas, which is what you want, of course. You don't want to be Harry Potter and experiencing all that acceleration. So if you try to remember what does acceleration mean, remember Harry Potter on his bus. That's called acceleration. Acceleration also means deceleration. That is starting or stopping. I don't care. The point is you're feeling it. And if you're not feeling it, it's not acceleration. So, so please do that. And with that, we will assign homework that I will post below this video. The homework is all the examples, and I will write down the homework below. I don't think I'll read it out loud here. That might be a way. Okay, fine, I'll read it. Example 3.12, 14, 15, 16, and then the homework page on page 243. I would like you to do problems 59, 61, 64, 68, 69, 70, 72, 73, and 75. And then I will, in a moment, talk about a couple of these problems, some of these problems, four. I decided to do four of these problems. So please go do your homework and then come back when you're done to look at some of the answers if you want.